The identity e to the power of I times pi equals -1 is not merely an algebraic curiosity. It is the geometric consequence of continuous compounding applied to rotation. The number e, approximately 2.718, defines the maximum rate of continuous growth. The imaginary unit I, defined as the square root of -1, introduces the dimension of rotation. Pi, approximately 3.14159, quantifies the angular displacement required for a half-turn. When these three constants interact, they force the system to land exactly on the real number -1. This visualization requires understanding how the complex plane transforms linear growth into circular motion, a concept rooted deeply in the calculus of infinite series. The complex plane, or Argand diagram, provides the necessary two-dimensional space for visualizing I. The horizontal axis represents all real numbers, while the vertical axis represents all imaginary numbers, multiples of I. A complex number z is expressed as x plus I times y, where x is the real component and y is the imaginary component. This structure allows us to define magnitude, the distance from the origin, and argument, the angle theta measured counterclockwise from the positive real axis. The unit circle is the locus of all complex numbers where the magnitude is exactly 1. Any operation involving I inherently involves a 90-degree rotation within this plane. The exponential function, e to the power of x, is uniquely defined in calculus as the function whose derivative is itself. Its Maclaurin series expansion provides the mechanism to extend its definition beyond real numbers. The series is the summation from n equals 0 to infinity of x to the power of n divided by n factorial. This infinite polynomial represents the function's value as the accumulation of increasingly smaller derivatives evaluated at 0. For real inputs, this series converges rapidly, defining exponential growth. To introduce rotation, we must substitute the imaginary input I times theta into this series expansion.
Before substitution, we examined the Maclaurin series for the trigonometric functions. The cosine of theta series uses only even powers of theta, alternating signs. 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial, and so on. The sine of theta series uses only odd powers of theta, also alternating signs. Theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and so on. These series are fundamentally linked to circular motion, describing the horizontal and vertical projections of a point moving around the unit circle. The alternating signs are crucial for generating the periodic nature of rotation. Substituting I times theta into the exponential series yields e to the power of I times theta equals the summation of I times theta to the power of n divided by n factorial. We analyze the powers of I. I to the power of 1 is I squared is -1, I cubed is -I, and I to the 4th is 1. This four-cycle pattern introduces the necessary sign changes and separates the terms into real and imaginary components. Grouping the terms with even powers of n, which are always real, reveals the Maclaurin series for cosine theta. Grouping the terms with odd powers of n, which are always imaginary, reveals I times the Maclaurin series for sine theta. This confirms Euler's formula, e to the power of I times theta equals cosine theta plus I times sine theta.
Euler's formula provides the polar form for any complex number on the unit circle. The term cosine theta plus I times sine theta is the definition of a point on the unit circle with an angle theta. The magnitude of this complex exponential is always the square root of cosine squared theta plus sine squared theta, which is identically 1. Therefore, e to the power of I times theta is a pure rotation operator. Increasing the value of theta continuously rotates the point counterclockwise around the origin. This complex exponential transforms the linear accumulation of the angle theta into the circular accumulation of position on the complex plane. The derivative of the complex exponential with respect to theta confirms the rotational motion. The derivative of e to the power of I times theta is I times e to the power of I times theta. Multiplying a complex number by I corresponds to a 90-degree counterclockwise rotation. This means the velocity vector, the derivative, is always perpendicular to the position vector, e to the power of I times theta. This perpendicularity is the defining characteristic of uniform circular motion. The instantaneous rate of change is always tangential to the unit circle, maintaining the constant radius of 1. demonstrating the fundamental link between calculus and complex rotation. To arrive at Euler's identity, we set the angle theta to pi radians, representing a half turn, 180 degrees. Substituting pi into Euler's formula yields e to the power of I times pi equals cosine of pi plus I times sine of pi. The cosine of pi is -1, as the horizontal projection lands on the negative real axis. The sine of pi is 0, as the vertical projection is 0 at this point. Therefore, e to the power of I times pi simplifies to -1 plus I times 0, which is simply -1. This completes the identity. E to the power of I times pi equals -1.
The visualization begins at theta equals 0, where e to the power of I times 0 equals cosine 0 plus I times sine 0, resulting in 1 plus 0i, the starting point on the positive real axis. As theta increases from 0 to pi, the point traces a continuous arc along the unit circle. The real component, cosine theta, decreases from 1 to -1. Simultaneously, the imaginary component, sine theta, increases to 1 at pi over 2, then decreases back to 0 at pi. The path is a smooth, continuous accumulation of angular change, terminating precisely at the coordinate -1, completing the half-turn rotation. The utility of the complex exponential extends far beyond pure mathematics, forming the basis of modern signal processing and differential equations. Any periodic function can be decomposed into a sum of complex exponentials using Fourier analysis. This is because the complex exponential is the unique eigenfunction of the differentiation operator. In electrical engineering, e to the power of I times omega times t represents alternating current signals, where the magnitude is the amplitude and the angle is the phase. This allows engineers to treat differentiation and integration as simple algebraic multiplication and division, simplifying the analysis of complex systems involving accumulation and change.